So we're going to move on to the second part of chapter 6, which is frames. So frames are a lot like trusses, but there's a critical difference. So if you remember trusses, uh, whoop, all right, trusses had the following characteristic, and that was all members are two-force members. Okay, so that means if we remember, let's say I've got a very simple truss here, just a few pieces. Naturally, put the supports in. When we go and draw the free body diagrams or disassemble it, let's say for the method of joints, each of the pieces is a two-force member. So that means that, of course, the force is aligned along the length of the member. And then on the other side it would look like that. So that's that's the critical one of the critical defining components of a truss, that all the internal pieces are two-force members. Frames look a lot like trusses, but frames are not, in general, made of two-force members. Okay. So frames are going to look a lot like trusses, but they're going to have three-force members and four-force and so on and so forth. Okay. So let's take a look at a device that looks like a frame, or that is a frame. All right. This is this yellow thing here is called a jib crane. Why it's called a jib crane, that's a good question. I don't know. I do know why it's called a crane, because it picks things up, right? So here's a cable, and it would have a weight right here. And then you could use this hydraulic cylinder right here to jack up the weight, so you would extend it up and it would lift this. This would go from being horizontal to being more vertical and lift up this horizontal crane member. Anyway, so it's got three basic parts. It's got this mast part right here, the hydraulic cylinder, and then this overhanging L crane part. So these type of things are used in moving medium-sized weights out of trucks, or in material handling during manufacture. Let's say you need to hold something up to fit it into place, to bolt together, or to weld, or something of that nature. Anyways, and in this particular one, it's got a cable. So this is a cable winch. So you turn this handle and it draws the cable onto this drum, and then this would move upwards if it had a weight on it. All right. So how do we analyze this structure? Well, we basically go through effectively two steps. We do a global equilibrium. So first thing we do is global equilibrium. So step one, global equilibrium. And this is basically the same as for trusses. So we want to figure out the reaction. So again, if we have this thing with a weight right here, W, then we draw the total free body diagram of this thing. So, whoops, that's not very good. All right. And this kind of comes down, goes vertical, right? And this kind of goes back up. Pin joint, and then there's a hydraulic cylinder. So this is a real big estimate of what it looks like. If we look, this thing is bolted to the ground, so this would be A. We'd call this pin joint at the corner there B, C, D, and then the load out here is E. So this would be A, B, the pin joint there would be C, the other pin joint would be D, and then this would be E right here. Okay, so we know what this looks like. Sorry, whoops. So we know this has a weight on it, so we'll replace that weight with, of course, the force. All right, so here's the W. We'd normally know geometry, L, something about the height, H, some other stuff. And then we can draw the reaction here at A. So AY, AX, and MAY, or MA. Right, so this is bolted to the ground, so the reaction at A is a cantilevered or a fixed reaction. And then we have the weight, and we know the geometry, and then so we can take it and go and using some moments and some forces equal to 0, we can solve for these reactions given given the weight applied. Okay, so once we have that, the next step is to disassemble the piece, right? So this is 3 pieces. So what we'll do is we'll break this into the 3 pieces. So there's a mast piece, the top of the crane piece, and then the hydraulic cylinder piece, which we'll just sort of model as a square. We got the reaction on the mast that we know about, AY, AX, and the moment, MA. So we've got those 3 things. We've already solved for those because that was that. On this one, we knew we had the weight, W, right? Because this is, let's call it this part 1. So that's this part right here, part 2, and that's that part right there, and this would be part 3, and that's the hydraulic cylinder right there, 3. Okay, and again, let me label this. So A, B, C, D, and E. All right, so now we need to account for all the internal forces, these pins, right? So we need to model this pin joint, and this pin joint, and this pin joint. So at E, right, or at B, sorry, we've got a reaction. So we've got BY, BX, and then down here at D, right, we also have a pin reaction. So we've got DY, and then DX. All right, so there's those things. All right, so now we do it on part 2. All right, so I'm going to draw them this way. And the reason we do that is Newton's third law, right? So if you notice, this is one side of pin joint B, the side that's attached to this mast, and it has BX pointing to the right. So on the other side of the pin joint B, the same thing that's on the inside here, the X reaction needs to point the other way, right? Because when you put both of these things back together again, it's not moving, so the force in pin B needs to be effectively 0 to keep it from flying, right? So this right here, those right there are a Newton's third law, right? Equal and opposite. So you'll need to, that's something in frames that you need to be careful of, keeping track of Newton's third law. Okay, so now on this side, right, we've got one more, we've got the reaction at C that we haven't talked about yet. And so CY, and then CX, and then the weight here is what we have. So now we can do CY, again opposite, CX on the horizontal, and then DY and DX. Sorry about the dog, everybody. The hydraulic cylinder is a 2-force body, right? So we know actually CY and CX, and this lies along the line of that, but we'll not deal with that for right now. Again, typically we know all the geometry, and then we could go ahead and use some forces equals 0 and some moments equals 0 on each individual piece to solve the equilibrium for each of the pieces. All right. So, in summary, the steps for frames are 1, global equilibrium. All right, so you do draw the free body diagram of the whole frame and then solve for the reactions that you can. 2, you disassemble. All right, and you got to make sure you're keeping in thought Newton's third. And then 3, equilibrium of each part. And so that means, right, some forces equal 0, some moments equal 0. And that's it. And then you'll have the solution for every single piece in the frame.